Our first paper is going to be given by Gabe Cohn, and it's Your Noise is My Command, this is a Best of Chi winner, which you may know is given to the top 1% of submissions. So many congratulations to yourself and your colleagues, and very much looking forward to your paper.
All right, thanks a lot. Again, my name is Gabe Cohn, and today I'm going to show you how your noise is my command. And that is how we can use the human body to sense gestures. Using the human body as an antenna to sense gestures in the home. So this is work that I did while at Microsoft Research, along with Dan Morris, Shwetak Patel, and Desni Tan. Now, this session is about gesture sensing. So why do we do gesture sensing? It's because as computing moves to be more ubiquitous and more mobile applications, we need to move beyond the mouse and keyboard. We need to find more natural ways for the user to interact with the computer. So one way is to use speech recognition. This works well in mobile applications, but it has a low input bandwidth, and it's not always appropriate in all situations. So for example, if you wanted to take notes while listening to my talk, it would not be appropriate for you to simply speak out loud while I'm talking. What you could do instead is use a capacitive touchscreen. This also works well in mobile applications, but doesn't scale well. Large capacitive displays are very expensive, and it's unlikely that all the walls in our home and our work environment will be soon instrumented with these large capacitive displays. So another idea, instead of instrumenting the environment, is to instrument the person. So last year at Chi, Chris Harrison talked about skinput, where you can turn your forearm or your hand into an interactive touchscreen by listening to the sound that your hand makes as it taps the skin. Also at Chi last year, Scott Saponis talked more about muscle-computer interfaces, where you can interact with the computer simply by moving your fingers. And this again works by instrumenting the body to listen to the electrical signals produced when your muscles fire. Now, these approaches work well, especially for mobile applications because it goes with you, but the problem is you can't really interact with your environment. So one way to do that is to put the instrumentation back on the environment and use something like computer vision or depth cameras. Now, this allows you to interact with your environment as long as you're standing in front of a camera. But if you move away from that spot, it doesn't work unless you have yet another camera. So what I'd like to be able to do is this kind of interaction without instrumenting the environment, so that I'm not pinned down to only working in the living room. I can do this kind of interaction anywhere in the home. So it could be in the kitchen, in the dining room, or in the bedroom. And I'm going to do this using the human body as an antenna. So in this work, we're going to focus on touch gestures. That is, every wall in your home becomes an interactive touch surface. And we can do this with no instrumentation to the environment and only minimal instrumentation to the user. So I've said several times I do this by using the human body as an antenna. So let me talk about what it means to use the human body as an antenna, and let me start with what is an antenna. So you might recognize this. This is a TV antenna. It's called a bunny ears antenna because of the way it looks. And it was designed specifically to receive the frequencies used for TV broadcasts. And now I'm going to show you another kind of antenna. This is a human body antenna. This one is called a teenager, again because of the way it looks. Only this one wasn't designed to operate at a certain frequency. It's actually just a dielectric with a complex geometry, and so it works fairly well as an antenna between about 40 hertz and 400 megahertz. Now, the fact that the human body can be used as an antenna is not a new idea. In fact, this is known in any kind of system that looks at signals on the human body, and it's actually a source of noise or interference. It's called the body antenna effect. And in this work, we're going to take this signal, which used to be considered noise, and actually use it to our advantage. Remember, your noise is my command. So let's look at our system. Here we have the human body antenna, and as we just learned, it will receive signals between about 40 hertz and 400 megahertz. Now for this work, we're concerned with signals below about 200 kilohertz. So what are the signals that are below 200 kilohertz that your body can receive? Well, in the home, this is power line noise, or the noise emitted from your power lines and the appliances in your home. Now this noise has been used for energy monitoring and activity recognition in the past. And in this work, we're going to use it for gestural sensing. So our hypothesis is that this power line noise differs at different locations in the home and different positions on the wall. And so since our human body antenna can receive this noise, we can determine the location in the home and the position on the wall of a user's touches. So in order to test this hypothesis, we built an apparatus to measure the noise that's received by the human body antenna. So we measure the voltage at 400 kilosamples per second at 16-bit resolution and store it to a hard drive that the user carries in a backpack. Now, as you can see, this is a large, clunky setup that we use for prototyping. But the important thing to notice is nothing fancy is going on here. This is just an analog digital converter. So it can easily be shrunk down and worn on something like a watch, for example. So using this apparatus, we put together an experiment where we recruited 10 participants, and each participant went to their own home to perform different gestures at different locations in the home in order to determine whether this works or not. So each user went to 6 different locations in their home. 5 of the locations were light switches. Remember, our noise source is the power line. So if they're going to interact around light switches, we know we're going to have a good noise source. We also chose one location where there was no central light switch in the middle. So we have no central signal source. But we know there's power somewhere in the wall because there's an outlet. And this will give us an idea of can we only interact around light switches, or can we also interact on arbitrary points on the wall? And 2 of the locations were in the same room. And this way we can determine whether we have accuracy at the room level in terms of the location of the user in the home or the sub-room level. Now at each location, the user would touch the wall in 5 places, shown as the blue dots on the screen. So one touch was on the light switch, one was above, below, left, and right. They also performed a 6th gesture where they simply didn't touch the wall at all but stood in front of it. Each of these gestures was held for 6 seconds, and the computer guided the user through the gestures. And at each location, the order in which they performed the gestures was randomized. So each user performed 6 gestures at 6 locations in the home, and this was considered one round. They would then start over and do the whole thing over again. And they did this 4 times. There are 4 completely separate rounds per user. So 144 total gestures per user, and we had 10 users. So we collected all this data, and then we went back to post-process it. Now if you take a look at the data, in the time domain, it looks something like this. Between the black bars is when the user was touching the wall. So as you can see, simply the amplitude of the signal changes significantly as the user touches the wall. So the first thing we did is we removed a ½ second at either end and took only the middle 5 seconds. And this removes any edge effects if the user was still approaching the wall or if they pulled their hand away too quickly. So if we zoom in on this 5 seconds, we then break this into many 82 millisecond windows. So all of our feature extraction and classification is done per 82 millisecond window. So let's zoom in on one of those windows. And in the time domain, we pull out 2 features. One is the DC, or mean value of the signal, and the other is the RMS, which gives an idea of the amplitude. Now, we know that this RMS is an important feature because, as we saw 2 slides ago, when the user touched the wall, the amplitude of the wave changed significantly. But there's other things that can be shown as well. If we look at the frequency domain, between about 0 and 200 kilohertz, we can see the 60 hertz peak. That's the frequency with which power is delivered to your appliances, and also the harmonics of 60 hertz. And those waves actually change significantly depending on where the user is touching on the wall. And this is because the radiation pattern coming out from the light switch is very non-uniform. And also, we can also determine somewhat the location of the user in the home just based on these peaks. And so we actually use all 332 of these raw FFT bins as features. If we look at the frequency band between 0 and 25 kilohertz, we apply a smoothing filter and then pull out 250 features. Oops. 250 features. Now these ones give us an idea of how quickly the harmonics of 60 hertz fall off. And this is also a function of where the user is and what gesture they're performing. If you look at the full frequency band, so 0 to 200 kilohertz, again apply a smoothing filter, and we're going to use 400 of these features. Now in this, you can see some of these high frequency peaks. Now these are produced by the appliances in your home, the switch mode power supplies that are in consumer electronic devices and compact fluorescent light bulbs. Now this is very useful for determining the location of the user in the home, because the amplitude of these peaks is going to vary depending on how close the user is to those appliances. We also identified 18 of these high frequency peaks, which were particularly useful for classification. And the same 18 peaks were used all across our data set, so every user and every home. So in total, we had 1,002 features that were extracted every 82 milliseconds. And we used these to train a support vector machine using the SMO implementation in Weka. And so all the results I'm going to show you on the following slides are using a 4-fold cross-validation. And we did a four-fold cross-validation because remember there were 4 rounds. Each user performed 6 gestures at 6 locations in the home, and that was considered 1 round. And they repeated that 4 times. Now these rounds were separated in time, so by folding across rounds, the training and testing sets are always in different rounds in order to avoid overfitting. So let's take a look at the results. So first we'll look at the simple problem is the user touching the wall or not? This is a 2-class problem, so the chance is 50%, shown at the blue bar, and our accuracy is about 98.5%. What's interesting is if we take only the locations where there's no light switch, or it was just a blank wall above an outlet, the accuracy doesn't change. So this gives us a hint that maybe we don't need to interact only around light switches. We can actually identify touches on arbitrary walls. So if we look at the classification of the user's touch point around the light switch, it's 5-class because it's the question of is the user touching the switch above, below, left, or right? We have an accuracy of about 87.4%. Now again, if we look at the location where there's no light switch, it's just a blank wall above an outlet, the accuracy drops to about 74.3%. This is still significantly above chance at 20%. And so, again, this gives us a hint that we don't need to interact only around light switches. We can actually identify arbitrary points on walls. So now if we look at the location of the user in the home, this is a 6-class problem because there were 6 locations in the home. And we get an accuracy of about 99.1%. Now this is very high, especially if you consider that 2 of the locations were in the same room. So this is actually better than room-level accuracy. If we take only the gestures where the user was standing near the wall, not even touching the wall, our accuracy doesn't change. So this tells us that we can identify the location of the user within the home without them even stopping to touch the wall. And we can do this with better than room-level accuracy. Now if we combine this location in the home and position of the hand around the light switch into a big 30-class classifier, we get an accuracy of about 80%. Now this may seem a bit low, but remember, this is an unoptimized classification per 82 millisecond window. And any touch is going to go over several 82 millisecond windows. So even using some sort of majority voting scheme, we should be able to increase this accuracy. So let's do a quick summary. In our core experiment, we had near 100% accuracy of the location of the user in the home, and about 87% accuracy of their touch position around a light switch. Now, we also performed an additional exploration in which we looked at other gestures and other parts of the phenomenon that's happening. And the details of this are in the paper. I'm just going to show you a few of the results. So we could also differentiate whether the user was touching with their right hand or their left hand. And we could also differentiate which appliance is being touched. So the core experiment only talked about touching walls, but you could touch appliances like refrigerator, oven, microwave, things like that as well, and we can differentiate which one's being touched. We can also estimate the continuous proximity of the user's hand to the wall, rather than is the user touching the wall or not. And the continuous position of the hand along the wall. So instead of saying the hand is above or below the light switch, we can say how far from the light switch is it. And these are great results. The question is, what are the limitations of this system? So one is, what is the generalizability of these noise signals? I mean, what kind of training procedure is necessary so this is going to work in every home with every user? How do we deal with locations in the home where our signals that we need for classification are low, or other signals in the home that interfere and wash out the signals we care about for classification? Also, how do we deal with the changing state of the home? We know from the past work in using power line noise for activity monitoring that when a user turns on and off an appliance, the noise in the power line changes. How will this affect our classifier? So the future work is, first of all, to address some of these limitations. And one way is to use an improved feature set. So right now, we only look at the absolute amplitudes in each frequency bin. If we instead look at the relative amplitude, or how the amplitude changes over time as the user performs a gesture, we can deal with a lot of these issues of the generalizability of the noise signal and the changing state of the home. We can also inject a signal, either into the body or into the power line, in order to deal with situations where the signals that we need aren't very strong or are being washed out by other signals. Basically, instead of just listening, we can put in signals that would help us. And then, of course, we can make a real-time system, make it smaller. Again, the backpack wasn't necessary. This can be made into a small device. And we can explore the contact to the body. So in this experiment, we just used the back of the neck. It doesn't need to be the back of the neck. If it's worn on the wrist, it could be the wrist. In fact, it might not need physical contact to the body at all. We could just couple to the body wirelessly. And then, of course, we can explore the gesture set and the application space of the work. So with that, I will conclude, and thank you for listening, and we'll open it up for questions.